So, at this time we are in a position to look at the experimental aspects. So, this is now becoming a little more critical from the point of view of what we can do from knowing all the rules of symmetry and the details of how the molecules arrange themselves in the given space group and so on. Obviously, the job would be to see where the atoms are and determine the positions of the atoms, and eventually find out how the atoms are connected to each other, look at their properties, and eventually relate the property of the crystalline material to the external physical property it exhibits. So, there are crystals which exhibit different kinds of properties. Some of them may be fast ion conductors, some of them may be pharmaceutically important compounds, some of them may be ferroelectric materials and so on. So, basically now is we get into the stage where we are now going to look at the experimental aspects in more detail. One of the major requirements which comes across is to grow a crystal, and we have to grow a good quality crystal. Now, growing a good quality of the crystal is in fact can be considered a rate limiting step, because very often some of the molecules have the property of not giving us good quality crystals. By good quality crystals, I mean the diffraction extending to as much extent as possible on the limiting sphere reciprocal lattice space. So, if you get as many reflections, then the issue of not having the required resolution limits becomes an issue. So, growing a good quality crystal therefore is what we will concentrate on. Of course, if a material does not grow into a good quality crystal, but remains polycrystalline, then the polycrystalline samples are also acceptable, because one can use the so called technique of powder diffraction. We will be spending a little bit of time on powder diffraction as well. So, apart from that, what is the experimental setup we look for? We can look for laboratory sources where we can have a tube X-ray or synchrotron radiation, which is available in several centers around the world, including the one in Indore in India. Then of course, we need a diffractometer, which is with a detector of a high quality. So, diffractometer is the one in which we mount the crystal on a goniometer and things like that. And then of course, we also need non-ambient attachments like low and high temperature attachments, high pressure attachments, and things of that kind, so that we can study the variation in the property with respect to these non-ambient conditions. So, particularly some of the compounds become highly conducting at higher temperatures, and some of the compounds at low temperatures show specific properties which are different from the room temperature property. Basically, phase transition studies associated with these materials will be of consequence. In context with the pharmaceutical industry, the requirement that the structure is known fully and its behavior is known in non-ambient conditions becomes an issue, because it depends upon how and why the crystals grow, and but the so called depiction of polymorphism associated with crystalline materials will also bring in the issue of dichotomy in pharma industry. So, considering all this is the basic experimental setup that is required, all these together, and of course, we can either have a good quality single crystal or a polycrystalline sample. Now, what are the methods we use for growing crystals? One is the solution methods, where in principle we take the material and then dissolve that material in a solvent, and then eventually control the evaporation of the solvent. This is the usual approach, which is shown here. So, we have a saturated solution, and then the crystals will start appearing depending upon the thermal reservoir. So, eventually the temperature associated with this we can control, so that the evaporation of the solvent is slow enough so that we get good quality crystals. This can be controlled in various ways. We can have more than one veil, more than one thermal reservoir, and things like that. So, this is basically the solution method. There is no time to in this particular course, we are not going to spend too much time on crystal growth mechanisms and so on. That is not the purpose of this, this particular course. However, we should know how we grow crystals. So, we have solution methods when the solvent goes away, or straightforward solvent evaporation. We can take the saturated solution, heat it up, or make a solution which is near saturation, and then just heat it up, evaporate the solvent, and hope that the crystals will form at the edges of the tube. The other approach is, of course, using solvent diffusion, allow the solvents to slowly diffuse out of the material so that crystals will form. Another approach is the so called sublimation method, where we heat the sample sublimes, and then you provide a thermal gradient along this tube, and this eventually we send in a coolant here, and then this is vacuum chamber. So, after the sample evaporates, it now condenses onto the tip here, which is carrying the coolant, and you will get crystals. So, this is the approach of sublimation, because in case the compound sublimes, this is a very good method to prepare good quality crystals, because now we can control the coolant temperature in such a way that the temperature associated with this can be monitored, and the size of the crystal can be controlled, size and shape of the crystal. The other approach, which has essentially developed in very few laboratories, and one of the laboratories happens to be our own, is the use of in situ cryocrystallography. Here what is done is there are lots of solvents which are used in crystallization process, and the solvent structure becomes therefore very important, whether it is having a certain property related to it, like the associated dipole moments and so on. If it is a subpolar solvent or a non-polar solvent, what is the influence of those solvents? So, in order to know about that, we have to crystallize the solvents themselves. So, one can crystallize the solvent by this procedure. What is done is the solution is taken in a capillary tube, and there is a thermal gradient which is created in such a way that at one time the solvent inside the capillary tube freezes and becomes a solid. Now, by repeated reorganization of this, like what they call as the zone melting, we keep melting the solid by providing a certain amount of heat, and again freezing it up. So, as this process is repeated over and over again, a good quality crystal will develop, as is shown here. This is a good quality crystal which eventually develops, and the quality of the crystal can be checked on a diffractometer by checking the diffraction spots which come out of this experiment. So, these are various methods. There are several others, but these are the basic methods which are essentially used. In order to crystallize proteins, there is a total new methodology. There is a total clearly different kinds of approaches. The material is taken in the form of inside a solvent, and then a drop of the solvent is made to hang on upside down against the gravity on a glass plate. And because of the gravity, eventually the material sort of sinks in, and you will get the crystal growth in the solvent drop method. There are several other methods. In fact, we can also have the zone melting, which is very, very popular among the metallurgists, where they can heat and cool the system. There are several apparatus that are available to grow quality crystals. So much that some of these methods will allow us to grow crystals which are very, very large in size. That brings us to the size of the crystal we want to use in our experiments. Most of the experiments which use X-ray diffraction would like the size of the crystal to be about 0.1 millimeter cube. So, we do not want any bigger crystals because of absorption of the X-rays within the material, and at the same time we do not want too very thin crystals because the quality of diffraction suffers. So, there is the optimum size estimated for either organic or inorganic materials is about 0.1 millimeter cube. In case the crystal is a big crystal, then we have to apply absorption corrections. In case the crystal is a very small crystal, then hardly diffraction comes. You see, the whole idea is to get the reflections in the entire reciprocal lattice frame. That means all possible reflections which come within the limiting sphere must be collected. The larger the data that we get, the better it is, and that is where we decide on the quality of the crystal. The quality of the crystal is not by the looks of the crystal, but by the extent to which it diffracts. So, as we discussed earlier, we discussed about the resolution limits. We calculated the value of d from 2d sin theta lambda, and the value of d now decides what is the resolution the data of the data we are going to expect by checking out what is the extent to which the diffraction occurs in sin theta. So, the larger the sin theta up to 1 degrees 1.0 sin theta value, the better are the data quality and also the quantity of data, that is both are required in order to do a good structure determination protocol. So, as we saw earlier also, this slide that it is taken from the book of Glusker and Trueblood, it is a old book, and that is how we have now shown here a photographic film. In that place we put now the CCD camera or the CMOS detector. So, what essentially it does is a comparison between a microscope and X-ray diffraction experiment. In case of a microscope, the object now sends scattered radiation. Here the radiation is following the Bragg's condition because it is a crystal, and all these Bragg's conditions will satisfy, we get the reciprocal lattice image. This reciprocal lattice image, the intensity can be measured, and the measured intensity now converted to the modulus of f of HKL, the structure factor. The phase problem is solved either by the crystallographer or by the computer, and then we do a Fourier synthesis. The Fourier synthesis will reconstruct the image of the object and in terms of the electron density distribution. So, we do get an electron density map, as we call it, and this electron density map not only identifies the positions of the atoms, in terms of its strength, it also identifies the nature of the atom, whether it is a carbon or a bromine or a nitrogen or whatever. So, that identity of the molecule can be obtained from what we call as the electron density map. So, this is the exercise we will have to do in the experiment, and normally therefore, this is the protocol. You grow single crystals, pick the best of the single crystals. We will see in a minute how we pick them up and how we mount them on this machine, which is a 4 circle diffractometer. This is an in-house diffractometer which we have, and this particular diffractometer we have several parts. The moving part is this part is the goniometer. The goniometer is mounted along this what we call as the omega axis, and on that omega axis the crystal can rotate, and therefore, we now identify the position of the reflection in terms of 4 circles. The circles are the rotation about crystal itself, which is the phi rotation, the rotation of the 2 theta arm, which is the 2 theta arm, the rotation of the 2 theta arm, that is theta. So, we have phi, theta, and then this is the angle which the goniometer forces itself to go, that is the kappa angle, and then the base plate rotation is the omega. So, we have therefore phi, omega, kappa and 2 theta. These are the 4 angles, and that is why it is called a 4 circle automatic diffractometer. This gives us the reciprocal lattice image. A good crystal will give very nice spots as is shown here, separated from each other. So, we now next have to do what is known as the indexing of this pattern, and once we do the indexing, we will get identity of each one of these HKLs, and we measure the intensity of each of spot. So, that is our data. So, once we have this data, we take it through the phase problem analysis and then the Fourier synthesis, we will end up with the electron density distribution, and this represents therefore the crystal structure. So, this view graph essentially tells you the basic experimental methodology one has to adapt for determining the structures. Now, the crystals can be of different shapes and sizes. Here are some of the crystals which are good crystals in appearance are shown here. These crystals are not so good in appearance, but they are also shown here just to tell you the variety of crystallinity we can impart on these materials. What is more important is not the appearance of good crystal or a bad crystal. What is important is this part, which is now the polarizing microscope view. So, if we put the crystal under a polarizing microscope and then move the polarizer, the Nicol prisms, in such a way that we will have an extinction of the light which is coming from this crystal. So, the crystal is in this orientation, different polarized light is now sent in, and as the polarizer is rotated, we will have extinction. So, if the complete darkness comes up, and again when we rotate another 180 degrees of the polarizer, we will get the crystal picture like this. So, this is very important before we decide to take the crystal onto the machine. So, if this is not happening and this remains same as, let us say, same transparency as is seen here with respect to light, then it means that the crystal is not a very good crystal. So, the crystal quality is tested under the polarizing microscope. It is not a guaranteed test, but basically it tells you the possibility of using that as a quality crystal onto the diffractometer. Now, on the diffractometer, on the goniometer, we can have different ways in which we can mount the crystal. One of the ways in which normally it is mounted is to take a glass fiber, and at the tip of the glass fiber use epoxy of some kind and then mount your crystal. This is a needle crystal which is mounted up here. If we are doing non-ambient crystallography and particularly variable temperature crystallography and so on, then the crystal has to be protected because we are going to change the temperature and pressure. So, for such a purpose we can enclose this crystal inside a capillary called the Lindemann capillary. This Lindemann capillary has the property that it will not absorb or diffract X-rays, and as a consequence they will just be the containers which hold the crystal. So, whatever comes out in the form of diffraction is that from the crystal. So, we get different signs of these Lindemann capillaries which can be mounted up here, and so that is, these are the two ways in which you collect the data. Of late the data collection, particularly if the crystal is small and also if the crystal is a protein crystal or whatever, we have these what are called the loops. So, this is a loop mounting with the help of a soil. In this particular case we use different kinds of materials. When you are doing, let us say, a data collection at 100K, you can use a soil which is now holding the crystal at this point, and then at 100K it will freeze. And this is essentially, it is oil, and the oil that we use is very special, and that particular oil, paratone oil. So, it is the paratone oil which we use in order to mount the crystal. So, we make use of the paratone oil and we mount the crystal on this loop. So, this is now the most common method which is used because there is no interference of either glass or any other material with the system, and also at the same time the crystal is now completely bathed in the incoming beam, which is a requirement for a quality diffraction. So, we will not go into the unnecessarily further details of experimentation because that is not the purpose. The purpose of this is to see what happens when we do the diffraction. So, we do the diffraction, and this is one of the CCD images which shows the reciprocal lattice images. So, these are the reciprocal lattice points which are seen here, dark and white. We know why some of them are dark and some of them are not so very dark or bright, as we have seen from our positioning of the atom with respect to the planes. So, having got this is one of the several hundreds of images which we can collect for a given crystal depending upon the orientation of the 2 theta, phi, psi and kappa. So, these 4 values, the 4 circles, now decide the geometry of the reciprocal lattice, which is now 3-dimensional in space. So, we collect the reciprocal lattice image which is 3-dimensional in space and make use of these, determine their intensities from the experiment by using a measurement technique, which is now converting these photons into electric fields in the CCD detector, and we measure the intensity directly. There are other detectors which one can use. The detectors could be image plates, the detector could be CMOS detector, which is essentially used in space technology, and CCD, which is very commonly used nowadays. Image plate is very commonly used in case of macromolecular structures because it is possible to wipe the image on the image plate before we re-expose. So, these are some of the advantages in an image plate where the reflections are very closely spaced. Those materials which are not so very closely placed can be collected both on CCD as well as CMOS. The time required and the amount of time we spend to collect each data point is pre-decided by us, and that depends upon the quality of the crystal and the extent to which we are looking for reflections in the reciprocal plane. So, if we want to go to the end of the reciprocal lattice dimension, which is the limiting sphere, we would like to have a good time of exposure, and this exposure time also depends, as we know, as we have already seen, on the f versus sin theta by lambda curve. So, at lower angles we will have higher intensities, at smaller angles, the larger angles we will have lower intensities. So, the exposure time accordingly we can change, we can go from a smaller 10-second data collection to almost a minute data collection if we are collecting at very high temperature and very high angular range. The other thing is, as we increase the temperature on the crystal, the the atoms in the crystal vibrate a little more than necessary, and those vibrations can cause the intensities to go down. So, on the other hand, if we cool the crystal, the spots become sharper. So, because the vibrations of the atoms are minimized. So, all these are experimental aspects which we have to optimize before we collect a good data set. Having got this kind of a thing, we start now with what we call as indexing. This is the backbone of the entire structure determination. So, this is a process which I have given a flow chart from the textbook of Bill Clegg, edited by Bill Clegg. Several other authors have written this. William Clegg is the editor of this particular book, which I will, of course, in the end of this course I will give all the list of all the books with their publishers, etc., with very special acknowledgements to each one of these authors who have written the books, because I have taken their pictures, their equations and their flow charts, as you can see here. This is something which we must be very happy about, because these are already available and we can use it for our presentation. So, the indexing process will start by collecting the data for several small parts of the reciprocal space. You saw in the previous picture a portion of the reciprocal space, and in this reciprocal space you see there are a few reciprocal lattice points which intersect the evolved sphere, and those which intersect the evolved sphere come up with intensities like this. That is how you see the spread. In the case where there is cell dimensions are very large, you see the spread becoming closer and closer. So, larger the cell dimensions, the spacing between these spots will be much closer. So, it is a reciprocal relationship. So, if the cell dimension is 100 angstroms like in a protein, then these spots will be very close to each other, whereas in this case it looks like a data from a very not so very strong reflecting material, and at the same time a smaller unit cell dimension. So, you collect the data from several small parts of the reciprocal lattice. So, do not keep the detector in one particular place. You change the angles, the other three angles, the phi, psi and omega. So, if you change the phi, psi, omega and then keep changing also the 2 theta, you can go in steps of 2 theta. Keep let us say collect data at 10 degrees, 12 degrees, 17 degrees, 18. You can program it in when you do the data collection protocol. So, collect the data from several small parts of the reciprocal lattice. So, we have a representative number of reflections, just as we saw in the previous view graph. We have a representative number of reflections coming from the same material in different parts of 2 theta space. So, having got that, you generate a list of vectors between the reflections collected. The vectors between the reflections collected, and then in such a way that you find 3 shortest non-coplanar vectors in the list. They should not be in the same plane, so it should not be coplanar, and then find among the set of spots which you have got, find the smallest or the shortest non-coplanar vectors from the list. It is believed that these 3 vectors will give us the trial unit cell. It may not be the correct unit cell, but you just select the 3 shortest non-coplanar vectors, and these 3 short non-planar vectors can be now used. They must be a primitive subset of the cell, if not the correct unit cell. This is something which we have to examine. So, to find 3 vectors which are non-coplanar, identify these 3 vectors as the trial unit cell. Once you find that out, you say, well, this could be the possible unit cell, some A, B, C, alpha, beta, gamma between them. So, these 3 vectors are taken as the trial unit cell. If this unit cell is a correct unit cell, using the trial unit cell, assign HKL indices to all other vectors. So, if you take this 3 as the trial unit cell, then you know the endpoints with these 3 vectors are defining now A, B and C. So, the endpoints with these 3 vectors are A, B and C. So, we now have the unit cell dimension and the interaxial angles between them, because we are identifying the vectors. So, using that you now assign HKL values to the rest of them. So, suppose this is 1 unit, 1 unit, 1 unit along A, B and C, and something else which is coming farther away could be a multiple of this. Something which is coming below this could be a fraction of that. But the chance of something coming shorter than this is less, because we have taken the 3 shortest non-coplanar vectors in from the list. So, these are the 3 shortest non-coplanar vectors. So, it could be a correct cell, it could be a not a correct cell, that is checked by this questionnaire here. Are all HKL indices integral values? So, once we have this, does it come the rest of the spots which we have? We may have 100 spots, let us say. The 100 spots which we have, are these HKL indices also integral values? So, we check on these HKL indices integral values, and if these integral values all appear to be good, in the sense you may not get exactly 145, you may get 1.2 at the most, and on the other side 0.8, then you can round it off to 1 effectively, or you may get 4, 7 and 8, for 3.9 and 4.1 and things like that. So, you give a tolerance limit within which all the HKL integers are integral. If they are really falling in that zone, then you say that you have determined the unit cell dimension. So, use these unit cell dimensions and do what is known as a least squares fit for this to identify the unit cell ABC. So, unit cell obtained and you stop it here. So, this is the indexing process. So, in the indexing process, the major requirement is that you have to now take every point in the reciprocal lattice for which you have measured the intensities, take those spots and then make sure that these spots are generated by 3 non-coplanar vectors, which are the shortest set of vectors in these representative 100 odd reflections. This can be easily done, programmed, and the machine will do this work. And so, once that is done, if they are all integers, it is fine. If they are not integers, then what you do is, if they come out as simple fractions, let us say 1/4, 1/2, then we can multiply by the 2 and 4 and then eventually decide this would be the cell. So, if many indices are simple fractions, then divide appropriate ABC by that fraction. So, you will get the new trial cell. Once you have the new trial cell, go back here and then again using the new trial cell assign HKLs, and now they will become all integral. If this process happens, there is no problem. But if this also fails, if you do not get a hold of it, then you can do 2 things. One is to collect more data and use the subset of present data, or try another indexing method, then repeat the cycle. There are different ways in which one can index the methodology. There are programs which are available, different kinds of programs, approaches it in different ways, and these therefore can be now put in such a way that we go back in and then again generate the list of vectors. So, this flow chart essentially tells us how to get to the cell dimensions. So, the way how to get to the cell dimensions and how to get the HKL values assigned to individual reciprocal lattice points. The appearance of the individual reciprocal lattice points thus is very, very important. So, when you have a good crystal, the appearance of the individual reflections should be as spherical as possible. It may not be always spherical, but as spherical as possible. That is because that will tell us that the crystal is rightly bathed in the beam of X-rays which are coming in, because normally the X-ray beam which comes out is a circular path. It has a circular diameter. It has got a circular circular shape which now falls on the crystal, and therefore, the reciprocal lattice points should mimic the shape of the incoming radiation. The incoming radiation is collimated normally. So, the X-rays which are coming from the various sources, they pass through a collimator. The collimator will adjust it to the size accordingly. So, we can change the size of the collimator. We can have 0.5 mm, 0.3 mm, 0.1 mm depending upon the size of the crystal. As the crystal becomes bigger and bigger, you can use bigger collimators, but then very big crystals are no, because they will absorb all the radiation which comes in. So, there is an optimized value again. So, normally the ones which are used on the routine diffractometer laboratory setup, the collimators are 0.05, and in some special circumstances 0.03 is also a used diameter for the collimator. So, once we have these HKL indices identified, the initial reflection list is generated, we have the unit cell. So, once we have the unit cell, now you collect a few more frames of data, that is reorient in different 2 theta directions and collect some more reflections. Use these cell dimensions. This is an additional check which we can do, which is not indicated in this flow chart. Use these ABC alpha beta values and then work out their corresponding HKLs. So, go backwards and determine the HKLs, and those should be integral values. This will now doubly verify the nature of the unit cell dimension which you have determined. So, the unit cell 3 vectors, non-collinear vectors will also have ABC alpha beta gamma information. So, the moment you have the first 3 shortest non-coplanar vectors as identified as a unit cell, you know the crystal system, because you know ABC, you know alpha beta gamma, so you know the crystal system. So, the crystal system is already identified by just doing a diffraction experiment and selecting the reciprocal lattice points in such a way that there are 3 directions in which the shortest vectors which will generate the rest of the reciprocal lattice points are identified. And this process can be repeated over and over again until the final ABC alpha beta gamma values are depicted on the screen. Once that is done, any data points you collect, you can go ahead and collect the full data, full sphere of data. Every lattice point in principle should be indexable. That means we can give a HKL value based on this ABC alpha beta gamma. So, that way this is a very useful approach by means of which you identified the cell dimensions.